We usually think about memory like a piece of office furniture. You experience something, and your brain files it away in a cabinet, just like a computer saving a document directly to a hard drive. But let's look at how these systems actually start. At initialization, you have a newly fertilized biological embryo and a brand new, untrained AI model. Inside these fresh systems, you won't find a single file, folder, or discrete memory. What you have is a vast, unstructured space of latent possibility, which leaves us with a real mystery. If an embryo and a blank AI model possess no stored instructions, how do they learn to function in a complex, demanding world? Imagine a high-dimensional space where thousands of data points move randomly and frantically with no discernible structure. This represents entropy. Entropy is a mathematical measure of extreme disorder, and it is the astronomical problem untrained biology and AI face. In this ocean of entropy, making random guesses is mathematically lethal. Almost every random action or cellular mutation leads to failure or death. So how do these delicate biological embryos and massive language models survive this chaotic void without saving specific step-by-step instructions to keep them safe? They survive because they don't try to defeat entropy by memorizing the world. Instead, they ride it. They harvest the chaos around them and ratchet it down into workable order. For living things, this process of adaptation happens through a mechanism known as epigenetics. Epigenetics is a biological process where the environment writes soft chemical instructions onto life forms. A cell is constantly bombarded by its outside environment. Incoming nutrient flows, harsh physical stress, dangerous chemical toxins, and developmental signals, all arriving at the cell wall demanding a response. Crucially, these external pressures do not mutate or rewrite the underlying sequence of the organism's DNA code. The genome stays completely intact. A flat, uniform topological plane slowly warps, dipping into smooth valleys while rising into steep hills. Environmental marks physically tilt the landscape of probability. Biological memory isn't a stored fact. It's an altered probability dictating how the organism will behave. In the digital realm, we see the exact same mechanical process in large language models. These AI systems are trained on vast amounts of text to predict and generate language. They manage entropy using a powerful technique known mathematically as backpropagation. Backpropagation is a method where a system calculates its errors and adjusts its internal weights. For an AI, the environment is its training data. Instead of physical nutrients or toxins, the model is hit with billions of text examples. And just like biological DNA, the AI does not rewrite its fundamental core architecture when it encounters this data or makes a mistake. The AI mathematically punishes its own errors by adjusting parameter weights. Specific connecting lines thicken and glow, while surrounding lines fade. An AI's knowledge isn't a text database. It is a biased pathway ensuring data flows differently the next time. Think of it like a river carving deep, intricate channels into the dirt over time. The river holds no diary of its journey. It keeps no record of where it has been. The memory of the past survives entirely in the physical structure of the newly carved channel. Neither cells nor AI models store photographs of reality. They internalize their encounters with the world as a permanent field of biased readiness. This means we have to redefine memory itself. Memory is a preserved asymmetry left behind by experience. Intelligence, therefore, is not the hoarding of trivia, isolated facts, or massive collections of data points. True intelligence is disciplined markability. It is the capacity of a system to let the universe leave advantageous marks upon it. Development, whether in a human child learning to speak or an AI model learning to predict text, is the process of wild, undirected possibility narrowing down into a highly constrained, capable form. Look at a fully formed adult organism or a fully trained AI model. You are looking at compressed past. They are the physical manifestations of generations of survival and billions of cycles of data. They have discarded the exact details of history. What remains are the biases and the structural scars necessary to survive the future. Which brings us to the nature of identity in any adaptive system. Identity is simply history held together long enough to act, and what we call memory is nothing more than the shape of the marks left behind.